what we are going to do in today's lecture, for the first half of today's lecture, we are going to look at some of the example problems for internal flows and a little bit about external flows, and then we will march on to the next topic of the course. So, the first problem is a tube in which a fluid is flowing at a mass flow rate of 0.01 kgs per second. Okay. Then the external surface is maintained at a constant flux of 2000 watt per meter square. Then the diameter is 60 millimeters. The mixing cup temperature at the inlet is 20 degrees C. It's 8 degrees C. Okay, oops, 80. Okay, the mixing cup temperature at the exit of the tube is 80 degrees C. So, obviously, you could imagine that the fluid is being heated up as it goes through the tube, and it is taking up heat from the fluid which is present around it. It maintains a constant flux of 2000 watt per meter square. So, the question is, what is the length of the tube? And the second question is, what is the surface temperature at L? Okay. So, if L is the length of the tube, what is the temperature of the curved surface at L? Okay. So, these are the two questions. Okay. So, how do we find this? Okay. So, the net amount of heat that is taken up by the fluid to increase its capacity, so that is given by m dot Cp into Tmo minus Tmi. Okay, so that is the net amount of heat that is taken up by the fluid under steady state condition. But that is also equal to the amount of heat Qs prime into the curved surface area, right. So, that is given by pi dl, right. So, that is pi into d into l. So, we have all the information. M dot Cp is given. So, I can put the numbers here. So, the length will be m dot Cp Tmo minus Tmi divided by pi into d, and that will be 0.01 into 4181 60 divided by pi 0.06 to 2000. So, that turns out to be 6.65 meters. So, I want you to stare at the numbers. Okay. By the way, this is a realistic set of numbers. So, look at that, the diameter of the tube is 60 millimeters. Okay. 60 millimeters is how much? It is this much, right. 6 centimeters is the diameter, and then the length of the tube is 6.65 meters. That is how much? That is almost the length of this dais, right, 6 meters. So, that is pretty high. So, this, if you actually remember your visit to RCS, you see the tube lengths that you have are very, very large in industry. The reason is, it takes a lot of effort to heat the fluid or cool the fluid, and therefore 6 meters is really not that much, and the diameter may be very small. In fact, most of the tubes that you saw for heating are probably not bigger than this. So, this is a pretty reasonable size dia for the tube, but then 6 meters is fairly long. So, the idea of heat transport is actually done along with the process. So when you do this process design and process flow sheet courses in the future semesters, you will see that the length of the tubing actually is a very, very important factor in designing how a plant has to be made. So you want to align your tube in such a way that you're actually minimizing the equipment, that is the tube size of the tube, but at the same time you maximize the amount of heat transport for a given system. So you can imagine that in a plant there will be many different fluids which is actually flowing in different directions to different equipments. Some have to be heated, some have to be cooled. So heat transport is a very, very important challenge, how to maintain the heat transport and so that you cut down the net energy cost. So that's an important challenge. It's important to understand, and if you get an alarming number of 6 meters, you should really not be too worried, because it's quite fair to have that long a tube and that thin a tube. Okay. Of course, if you do a reactor design, if you get a reactor size of 6 meters, you have to worry about it, because that's an impossible thing to do. It's very difficult to build a 6 meter tall reactor. I mean, there are reactors which are that tall, but really it's not a very standard thing to have a reactor which is that tall. So you have to have some feel for the numbers. If you have a piping system, 6 meters is reasonable. But if you have a reactor, you cannot have a 6 meter tall reactor. It's very difficult to maintain it. Okay. So you must have some feel for numbers while you go through some of these problems. And most of the problems in the text are fairly realistic. These are industrially related problems. So it gives you a good feel of the different kinds of numbers that you will encounter when you go to industry in the future. Okay. So the second problem is how to find the temperature of the surface at L. How do we do this? How do we find the temperature? So it's a constant flux condition. Yeah. Heat transport coefficient. Okay. That is not there. Right. We don't know that yet. So we know that, supposing I write the Newton's law of cooling at L, so where Qs at L will be sum H into Ts minus Tm at L, right? So that's the Newton's law of cooling at L. Now, if I know what is the heat transport coefficient and what is M, I'm done, right? But I know much more than that. Okay. So it's a constant flux condition. I know what's the temperature profile of the mixing cup temperature, right? So I know that Tm is given by Tmi plus, yeah, Qs double prime into P divided by m dot Cp into x. So Tm at L is given by Tmi plus Q double prime P divided by m dot Cp into L. Right, so we know this. Okay, so we can use this information, and then we can also find, I have not given other numbers here, so we can also find what is Nusselt number. What's Nusselt number? The constant flux case. Now if I assume that it's fully developed, what's the Nusselt number? It's constant, right? It's a constant, and it's 4.36. Okay. So from here I can find out what is the heat transport coefficient, 4.36 into K by D. So that's the conductivity of the fluid, Kf, the conductivity of the fluid divided by D. So from here I should be able to find out what is the heat transport coefficient, right? So if I throw in these numbers, there will be 48.7 watt per meter square Kelvin. Now, how do we know whether it is really fully developed or not? X by D in the fully developed regime. Okay, if this is 0.05 times Reynolds number times Prandtl number. Okay, so that's, if this is satisfied, then you can assume that it's a fully developed system. Okay, so we can calculate the Reynolds number and Prandtl number. So Reynolds number is about 603 and Prandtl number is about 2 or something like that. Okay. So it will be much higher than the x by d. So when this condition is satisfied, in fact that was one of the things we discussed when we started the discussion on convection and internal flows. So if this condition is satisfied, then you can assume that it's a fully developed system. And so therefore the Ts at L, okay, so that's given by Us prime divided by H plus Tm at L. Okay, so that's given by 2000 divided by 48.7 plus 80, so that's about 121 degrees C. Okay, so that's the temperature of the surface at x equal to L. Now suppose if it is water, okay, I didn't tell you which fluid is going inside. Suppose if it is water, is it a reasonable temperature? No. Why? It's above the boiling point of water. So supposing the fluid that is going inside is water, okay. Suppose it's water, okay, then Ts of L equal to 121 is quite unreasonable. So you would expect that the water would have actually boiled at that time, you will see vapors. So all your calculations will fall apart. So you have to pay attention to the temperatures that you get. If you assume that it's a single phase, so note that we never looked at multi-phase system as of now. So we've assumed that there is no phase change in the fluid as it goes through the tube. So you have to pay attention to these numbers. You have to make sure that these numbers that you get are not above the boiling point of the fluid that you are actually looking at. So if this has to be correct, then it cannot be water, it has to be some other fluid. Okay, so it's important to pay attention. The point is that you have to pay attention to the numbers that you get. It's very important. Okay? Alright, so let's go to the next problem. We have a tube and we have a fluid which is flowing through it 0.05 kg per second, and the diameter is 0.15 meters. And let's say there is a fluid which is flowing past the outer curved surface and it's at 0 degree C, and the external heat transport coefficient is 6 watt per meter square of Kelvin. Okay, and then the Tm at L is 77 degrees C, and Tm 0 is 103 degrees C, and the length is 5 meters. So the question is, what is the heat loss over L? So the question is, see, supposing I look at different x values, okay, at which the fully developed regime is going to appear. Okay. So I just want to make sure that for most of the tube it's fully developed, that's all. So the entry length is very, very small. So the Nusselt number, if you look at the Nusselt number that you got for the correlation that you got when you included entry length, is always the Nusselt number will be Nusselt number for fully developed plus some contribution. But it's 7 meters. The total length is 7 meters, very small, right? So if you notice the Nusselt number correlation, you will always see that it's Nusselt number fully developed plus some contribution because of entry length. So if this contribution is insignificant, so you assume that it's almost constant, that's all. Okay, so here the question is, what is the heat loss over the whole length of the tube, and what's the flux and what is the temperature distribution, temperature at L, okay, and some numbers are given here. So, Prandtl number is 0.7, N is 0.3, okay. So, how do we go about calculating this? So, first one is easy, it is MCP delta T. So, Q is m dot Cp into Tmi minus Tmo minus Tmi, and that is equal to, put the numbers, 0.05 into 1010 into 77 minus 103. So, that is minus 1313 watts. Why is it negative? Because the fluid is now losing heat to the surroundings, right. So, that is the sign convention that we have used. Okay. Then what about how do we find Q double prime? Flux of heat that goes from the fluid inside the tube to the fluid outside the tube. Okay, I will give you a hint, okay. So, you can look at it in a slightly different way. So, remember what you have learnt in your conduction topic, okay. So, if you have a wall here, yeah, okay. So, the way to see that is, suppose you have a slab, okay. Now, there is one fluid which is flowing here, there is another fluid which is present on this side, okay. So, now the flux of heat transport, whatever flux of heat transport is essentially what is transferred to the wall, and from the wall it is transferred to the fluid outside, okay. So, if I assume that the resistance offered by the wall is negligible, so I assume that the resistance offered by wall for conduction, okay, I should also mention conduction resistance, is not a very bad assumption to make, because if the thickness of the tube will be typically very small, and also the conductivity of the solid is significantly higher than the conductivity of the gas stream that you have or the fluid stream. Therefore, the conduction resistance that is offered may not be that significant compared to the convection. Yes. It will be the same. It just makes your calculations easy. That's all. You can always include conduction. It's not a big deal. It's very easy. It's just sticking one more extra resistance inside. That's all. So, what I can simply do is now I can construct a resistance network. Okay, and what's this resistance? This is the temperature inside the tube, and this is the wall temperature, and this is the temperature of the fluid outside, okay, and this is 1 by H inside into A, is 1 by H outside into A, okay. So, that is the resistance. So, if we know the heat transport coefficient, I am done, because I know the mixing cup temperature. So, the representative temperature here is the mixing cup temperature. So, if I know the temperatures, if I know the heat transport coefficient, I am done, okay. So, now the question is to calculate the inside heat transport coefficient. Outside heat transport coefficient is given, we just have to calculate the inside heat transport, okay. So, that is what we are going to do next. So, we say we are going to calculate the Reynolds number. Reynolds number is 4 m dot pi d mu. So, that will be about 20404. So, clearly it is a turbulent flow, turbulent conditions, and so we have to use the Dittus-Boelter equation. We have to use the Dittus-Boelter equation to find the Nusselt number. So, Nu based on D is 0.023, Reynolds number to the power of 4 by 5, Prandtl to the power of 0.3. So, from here we find that will be 11.6 watt per meter square Kelvin. So, that is the heat transport coefficient at L. So, now using the resistance network, Qs double prime is nothing but the overall temperature difference divided by the resistance, right. So, that will be Tm minus T infinity at L divided by 1 by Hi plus 1 by H naught. So, remember I am calculating flux, so I have removed the area. So, if I know H and HO, I am done. I know what is TML, I know what is T infinity. So, I can just plug the numbers and this will turn out to be 304.5 watt per meter square. Okay. So, that is the flux. How do I find the next question is I need to find the temperature at the boundary. I need to find Ts. Okay. So, I need to find Ts at L. How do we do that? Yeah, so same flux. So, Qs double prime is also equal to TML minus TSL divided by 1 by Hi. Okay. So, from this I can calculate Tm of L, it's equal to 550.7 degrees. Okay. So, that is the temperature at the of the fluid at the location where the fluid is leaving the tube at L. Okay. So, remember that the resistance concept that we actually developed and discussed in conduction topic actually comes very handy. So, when you have simultaneous conduction convection processes, if you do not have any heat generation in the wall, which is not a bad assumption to make, you can see that these resistance concepts you will start seeing that it is coming in again and again in many different scenarios. Okay. So, that is a very, very important tool to learn the resistance concepts which was also used in radiation. So, this aspect of using resistances to calculate different properties is an important and very, very useful practical tool. Okay. Alright, so let us look at another problem. So, once again we have a tube, okay. Then now instead of having constant flux, we have a variable flux, but a known variability. Okay. So, we say that it's some maxima multiplied by sine pi x by L. So, L is the length of the tube, x is the axial direction, and m dot is the rate at which the mass is flowing through the tube, and Tmi is the temperature, mixing cup temperature at the inlet, and Tmo is the mixing cup temperature at the outlet. And if we assume that Qsm, which is the maximum flux, and that remains constant, we assume that the maximum flux is present somewhere in between, and we assume that that maxima remains constant, and so we have a known function for the flux. So, the question is, so if heat transport coefficient is constant, which means that we are really looking at fully developed regime, if the heat transport coefficient is constant, how does mean temperature and surface temperature vary with x? We said that dTm by dx is nothing but Qs prime into perimeter by m dot c. Okay. So, that is the balance for the mean temperature or the cup mixing temperature, and so we know what Qs is. So, we substitute Qs as P into sine pi x by L divided by m dot Cp. So, we integrate this, we get it very easy. Okay. So, we find that Tm at x minus Tm at the inlet, that is equal to pi d, which is the perimeter, pi divided by m dot Cp integral 0 to x sin pi x by L dx. That gives you the expression for the mean temperature as a function of x location. How do we find the surface temperature? Easy again. So, we know that Qs prime is h into Ts minus Tm, right. So, you just plug in the expression for Tmx here, we will be able to find it. So, it is very easy. Okay. So, really if you start from really basic first principles and try to understand what is being asked and how to go about finding it, most of these problems will actually fall out if you do it systematically. They will all fall out very easily. Okay. Alright, so I think we will finish the internal flows topic with this example, and after a quick summary we will go to the next topic. So, what we have looked at so far is, first is we started with the boundary layer analogies. We looked at boundary layer analogies and we looked at Reynolds and Chilton-Colburn analogy, which is also called as modified Reynolds analogy. With that we moved on to forced convection. We looked at heat transport and mass transport when there is fluid which is being pumped by a pump, or it's a pressure driven flow, and in this case we looked at external flows, and we looked at flat plate, we looked at cylinders, and we also looked at laminar turbulence in both these cases. Okay. And then we moved on to internal flows. Really pipe flow is what we looked at. We looked at pipe flow and we found the characteristics, or I should say nature of heat transport coefficient, nature of H and Hm, we found that, and then we looked at correlations for laminar and turbulent. Okay. So, that is all we have covered. So, next what we are going to move on is the next topic, which is the free convection or natural convection.